Hello students, next we'll look at continuous time LTI system and convolution integral. So we have studied what is convolution sum. Now we are going to study the case of convolution integral. Of course, convolution integral happens in the case of a continuous time system. Continuous time system is different from discrete time system. Up till now we had studied discrete time system. Now we are going to study continuous time LTI system and the convolution integral that is there in it. The first thing that we have already studied previously in discrete time also is that if suppose you are having a system, and let me write here, if you are having a system and if you want to find out, what is the output of a system, which is generally y of n, when you give a particular input, then you should know the system. And one way to know the system is if in place of the input, this continuous time, so I should not write y of n, I should write x of n. So y of t. So x of t, if you are going to put an impulse signal, that is delta of t, then y of t will be equal to h of t, where what is h of t? H of t is the system that you are having. So one way to get h of t is to basically input a impulse signal. This we basically write it as h of t is basically the transformation of an impulse signal delta t. So we should write this as a statement. So we say the impulse response h of t of a continuous time LTI system is defined as the response of the system when the input of the system is delta of t. So now if we have got the output, that is the impulse response, if we have got of a system, that is h of t, if we know, then what will happen when we will give any particular input x of n? So basically what we want to find out is response of continuous time LTI system to any arbitrary input. That means if I am going to give any x of n and I already know h of n, then how do I basically find, if I know x of t and it's already continuous time, so I should take care now. So if it is h of t and I already know that the input signal is x of t, then how do I find out y of t? And basically what you will find out is that y of t will be basically given by x of t convolution with h of t. But here now it is convolution integral. So that is something that we have to derive here. Just like we did in the case of discrete time, we have to derive that here. Now, we have already known the properties of the impulse function. Okay, so we know from definition of impulse function, from definition of delta t, we already know that if you are integrating any function phi of t with delta, let's say shifted to a value t minus t naught dt, we have already studied this, that if you if you consider anything within the time minus infinity to infinity, it's as good as finding out the value delta phi at t naught. So basically what this means is, suppose if you are having a signal, let's draw the signal like this, and you are having an impulse function, and we know how we draw an impulse function, we draw it with an arrow, but generally it is at 0, but now since it is shifted to t naught, let's say this is delta t minus t naught. We know that if we multiply both of this signal, I will basically get this value. That's all. And that is what is exactly what they mean by this equation, that you will get the value of, this is phi of t. You will get the value of phi of t at t naught. That means this value is phi of t naught. How do you get it? Obviously, when you multiply this with this and then you integrate throughout, rest all of them become 0. Only what remains is this value. And this is something that we have already studied in the definition of the impulse function. Then we can say, then for any arbitrary function x of tau, so now I am going to take for any arbitrary function x of tau, I can use the same principle that if I am going to integrate it from minus infinity to infinity x of tau, so now the time axis is changed, okay, x of tau delta tau minus t naught, delta tau minus t naught into dt, then it will be as good as finding out what is the value of x at t naught. This we should always remember. Now instead of t naught, if I write t, that is also okay. So I don't write t naught, I write only t. Okay, I write only t. Now we also know that delta of t is same as delta of minus t. That means it is basically a even function because it has only value at t is equal to 0. Therefore, we will be able to say that delta of tau minus t will be equal to delta of minus of tau minus t. Correct? Which is what? Which is equal to delta of t minus tau. So I am going to substitute that here. Instead of tau minus t, I can write t minus tau. That is what basically it means. So therefore I can write, therefore integral minus infinity to infinity x of tau delta of t minus tau is equal to x of t. Correct? So what is this equation? This equation, which I will now name it as equation number 1, this equation helps us to see x of t as a combination of, as a integral equation, What does that mean? It means that what it is trying to say is that you can have x of t by basically having, suppose if you want to draw x of t, this is suppose x of t, then it is as good as you are imagining that it is made up of many very close lying impulse function, very close lying impulse function, all of same height. Okay, they are but of same height. If you multiply both of this, now if you consider only one impulse out of that, it is basically giving us this value. Similarly, the one that is closely lying next to it, that will give us the next close value. So it is very close value. So I should write here dt. I should not miss out dt here because it's very close value. So it is very, very close. It should be d tau actually because it is with function tau. So it is d tau. D tau. So you can see that basically any signal x of t can be written as a combination of very closely lying impulse function multiplied with the original x of t. So this is the very close lying impulse function multiplied with x of t, and when you do the integration you get this. See, this is similar to what we did in dt in discrete time. If you would remember, instead of summation, instead of integration, we had summation x of n delta n minus n naught. The same thing is what we are basically having here, but instead of being a discrete time, it is continuous time. That's why you are having a integral equation. So this helps x of t to be seen as an integral equation, and this we will use as we move forward. Now we know that the output of a system, now we know that y of t is basically the transformation of the input signal, which is x of t. But x of t we have already seen in equation 1. So that equation then becomes integral minus infinity to infinity x of t, x of tau, delta t minus tau d tau. Correct? Now I am going to transform only what is, I can transform only what is there in with respect to t. I cannot deal with tau. So what I will do is I will basically take the tau terms outside. So I can write minus infinity to infinity x of tau, that is taken outside, even d tau is taken outside, and then transmission or the transformation of delta t minus tau d tau. Correct? So now t is acting only on that function which has t, no tau. So only t here is delta t minus tau. So the transformation of delta t minus tau. If that is the case, then I can write, so let me write that equation again here. Y of t is equal to integral minus infinity to infinity x of tau transformation of, let me write it neatly, transformation of, let me write it in a different color also, because then it will become more clear. So transformation of delta what I had written, delta t minus tau. So delta t minus tau, then the remaining d tau. But what is the transformation of delta t minus tau? Look here, we have already seen that the impulse response means that if you are going to transform any impulse signal, you will get h of t. That means if you are trying to transform delta t minus tau, then the transformation of that will be basically h of t minus tau based on this equation. Correct? So the same thing we will use here. So the same thing we are going to use here. So we will write but transformation of delta t is h of t, therefore the transformation of delta t minus tau should be h of t minus tau. Okay, so therefore y of t now changes to minus infinity to infinity x of tau, and instead of transformation of delta t minus tau, I will write the impulse response h of t minus tau d tau. And this equation is the basic equation of convolution integral. This is the equation of convolution integral. Previously we had convolution sum, now we are having convolution integral for the case of continuous time signal. So in the case of CT, we are having convolution integral. For the case of DT, we are having the convolution sum. And this equation is now to be used whenever you are having the value of input x of t and h of t, and you want to find out what is the output. So this is the basic equation that you do. So is there any way to write? Yes, there is a way to write this. This is y of t is equal to x of t convolution with h of t. So if we are having a system which is defined as a system having a function which is h of t, and we give an input signal which is x of t, then we will get an output which is y of t, which we can now write. So if this is x of t, the output y of t can be written as the convolution of x of t with h of t, which is not multiplication, it is convolution. And y of t equation, if you are asked what is y of t equation, then it is summation minus infinity to infinity x of tau into h of t minus tau, h of t minus tau. And that is what is the derivation that we have basically done from, from top to bottom, and we have got this particular result. Now you might seem to follow that. See, there is a y of n. In case of dt, it was y of n summation of k is equal to minus infinity to infinity x of k h of n minus k. It is somewhat similar, not somewhat, it is almost similar, where instead of summation you are having integration. See, here the summation was based on k, here it is with respect to tau, so I should write d tau. It is with respect to d tau. So this difference is the only difference that is there. Otherwise it means one and the same thing, that you have to convolute between x of t and h of t. So now we have to see a problem of how we basically carry out the convolution. The method is similar but slightly different for the case of continuous time. Now look at this particular example. If x of t and h of t are as given in the figure below, find the output y of t. So we know that the equation for finding out y of t, so I will write here, we know y of t is basically integral minus infinity to infinity x of tau h of t minus tau d tau, which I can write as minus infinity to infinity x of tau h of minus tau plus t dt. Okay, so with respect to changing value of not dt, d tau. So with respect to changing value of t's, I can find out the same equation. So now how do we do it? The first thing is we redraw x of t as such. So x of t is drawn. Next, below that we will draw h of minus t. So we have to flip h of t. Now there is no need for me to especially say why we have to draw h of t in flipped form, because you have already studied that in the previous case, isn't it? So there is no point in repeating that thing again, why we have to flip it. So here we are having h of t, and when we flip h of t, whatever is in the positive axis, that will come in the negative axis. So this is what is going to be. Okay, so this is h of t, and I will write this as the, so I should take care that I should not write x of t now, because based on equation this is x of tau, this is tau, and this is h of minus tau. Okay, this is 2 0 and this is minus 2 and the height is 2. Now we are going to start from here, and for different values of y of t we are going to make the changes. Now here what I would always recommend is that you shift the signal such that the starting end of the signal, which is the starting end of the signal, this is the starting end of the signal, and the the leftmost part of the second, that is x of t, they both are in the same axis. That means what I will do is I will basically draw h of t in such a way that, okay, let me draw it again. So if this is tau, then I will try to draw the h of minus tau in such a way that now it is not going to be h of minus tau. I am going to shift it towards this side such that the end, the rightmost end of the pulse or the signal what we have drawn, that meets with the leftmost end of the signal. That means what I am trying to share here is that these two are now in a line. So now from here it is ready to go inside. So if the original signal h of minus t was basically like this, and then I flipped it, when I flipped it I basically got the signal, suppose like this. So this is h of minus tau. Then how much I have to shift it here? Now we know that if we have to shift it in the left side, then because the time axis is already reversed, then I have to write minus of some t. So how much I have to shift here so that it comes at this point, and that point is which point? That point is minus 2. So if it has to come to minus 2, then obviously I have to write here minus 2. Correct? So that initially what was in 0 is now shifted towards left, such that the leading edge or the leading part of the signal x of tau is meeting in the same axis with the last end of the signal of h of minus tau. So that is how the signal is going to look like. So now this is h of minus t minus 2. So basically I am going to start from y of t minus 2. Now when I am going to multiply, I will get y of t for t, if I have taken minus 2, so t less than or equal to minus 2, the value of y of t is going to be always 0, because the multiplication of both these signals, will always become 0, and the integration of that will give me a value 0. Because its value is going to be 0, y of t is going to be equal to 0. Now I have to shift. See, now when I am going to shift, the signal is going to look like how the signal is going to look like. Now look at this representation that I have drawn. Here I am having the signal. X of tau and h of t minus tau, and what I have to do is, when I move this value of t here, t is right now minus 2, when I am going to move this value from here, slowly towards the right. Now when both these signals multiply, what will happen? Now when I look at the signals and both of them multiply, I will get the multiplication as a signal which is basically going from here to here. But when I say that, you have to be very careful. When I say that, this is slowly moving inside, isn't it? This is slowly moving inside. First it will be this much. So if I am going to multiply both of this, I will get the value which is basically, like this. So this is the multiplication of the value, which is the multiplication of both of this. Since this is also 2 and this is also 2, so 2 into 2, the height is going to be equal to 4. And then if I am trying to find out the integral, if I am trying to find out the integral of this x of tau multiplied with h of minus tau minus 2 throughout, then this is the multiplication factor, and if I try to take the integration, it means I am trying to find out the area. Now this signal has moved from minus 2, it has moved from minus 2 to minus 1, so this is from minus 2 to minus 1. So the width is 1, the height is 4, so the area that I am going to get here is going to be equal to 4 into 1, which is equal to 4. So the value is going to be 4, isn't it? But my movement is very small. My movement is step by step, step by step, step by step. Then how do I do that? That is what is basically the one thing that everyone has to take care. See, there will be a time when my signal is here and the multiplication is 0. When my signal is moving slightly inside at some particular value of t, that time the pulse of the width will be only this much. So I have to find out the area of this much. And slowly as this signal is moving inside, the area will slowly increase, isn't it? The area will slowly increase, and that is what that is what people have to take care. So slowly the area will keep on increasing until it reaches here, because at this point what will happen is, if I am going to totally take this one out, at this point now the area is different. How do we calculate that? At this point the height is going to be 4, no problem. The multiplication is now going to be from minus 2 all the way up to 0. Okay, and now if you would try to find out the area here would be 4 into 2, which is going to be 8. So the area starts slowly from 0, it goes all the way up to 8. So it slowly moves, the area slowly changes and goes up to 8. Then what happens? Then when I am going to move this signal further, now whatever be the case, the area is going to be 8 only. Why the area is going to be 8? Because in this case, let me rub it. In this case, the signal will basically start from this point, from this point, it will go all the way up to 4, and it will remain like that up till here. And this width, since this width is always equal to 2, so this width will always become 2. And the height is always 4, so now the area is going to be 8. So it went from 0 to 8, and then it continued to be in 8 up till when? Up till this particular pulse totally moves out. That means up till this particular pulse slowly comes and reaches here. Because then if I am going to draw the pulse, then the pulse is going to look different, because it will start from 0, it will go all the way up, the multiplication will be 2 into 2, 4, and then it will come down. Here also it will be 8, because the width is 2. But then after that, as the signal slowly moves out, the area that is going to be there, that is going to change, because this end is not going to be there, and basically the signal will look that it will start from here, it will end up till here, because this is the point. In between this only we will have the multiplication, and now the area is small than 8, and this will keep on happening until this signal slowly moves out. So as it moves out and as it reaches here, the signal will basically become 0. So basically it will go from 8, slowly it will go down and it will again become 0. So if I am going to see that, then the signal as it moves from this point, so this point is what? This is -2, and if this signal has to reach here, then it is going to be moving all the way up to this point is going to be +2. Okay, so if that is +2, that means the signal has gone. If that is +2, then this is basically +4. Okay, that means the signal has gone originally from -2, so this is -2. This signal has traveled almost up to +4. That means it has gone all the way up to 6. That means if I am going to draw my y of t, if I am trying to draw my y of t signal, the y of t signal will be slowly rising from -2. So from up till -2 it will be 0. From -2 it will keep on slowly rising up till this reaches here. Where does this reach? This reaches, basically this signal reaches here. So by that time, so when this signal reaches here, that means the signal has reached 0, because this has reached 0. So up till that, slowly the area will increase and your y of t will also increase and it will reach here. Its amplitude here will be 8, and then the signal will basically move like this. It will move up till here also, it is also 8. That means when it reaches +2, so when it has reached +2, up till +2, its value is going to be 8. And then when the signal slowly moves out, its value keeps on decreasing until it reaches 4. So its value keeps on decreasing until it reaches 4, and then basically its value goes straight. Again it's going to be 0. So this is what is going to happen at the output. So the value will be 8 here, it will be -2 here, and here it will go all the way up to +4. All the way it will go up to +4, and this will be to +2. So this is what is going to be the output going to look like. You can check it. See, you should remember the equation is -∞ to ∞ x of tau h of -tau plus t. This is what the equation is for finding out y of t. So for different values of y of t, which is basically the shift, for different values of t, which is basically the shift, as the signal moves from here, slowly it moves inside. For each and every small value of t, that's tau, that means for the whole tau we are going to multiply the signal and we are going to integrate. That means we are going to find out the area of the multiplication, and that value will slowly go from 0 to move up to 8 once this signal reaches here. Once this signal reaches here, after it reaches there, then the multiplication is always going to be the same. That means the area is going to be the same for up till this signal reaches here, and that is +2. Once this signal reaches here and then it goes out, slowly the area will keep on decreasing until it moves out, and you will get this signal. But how to get it is something that we will see in the next video, because you have to see how mathematically you will be able to solve this. So up till now I will stop here, because now itself it's almost half an hour video, and the next part I will ask you to study in the in the next video. I will show how to write it and get this answer. Thank you.